Welcome back, listeners. This is Continuous Improvement, the podcast where we explore the fascinating world of technology and how it's constantly evolving. I'm your host, Victor, and in today's episode, we're diving into the CAP theorem and its implications on distributed system design. But before we begin, let's quickly recap what the CAP theorem actually is. Formulated by computer scientist Eric Brewer in 2000, the CAP theorem explores the inherent trade-offs in achieving consistency, C, availability, A, and partition tolerance, P, simultaneously within a distributed system. Now, let's break down each aspect a bit further. Consistency refers to all nodes in a distributed system having the same data at the same time. Availability implies that every request made to the system must receive a response, regardless of the system's state. And partition tolerance addresses the system's ability to continue functioning even when network partitions occur, causing communication failures. According to the CAP theorem, it's impossible to guarantee all three aspects simultaneously in a distributed system. It forces designers to choose between consistency and availability when faced with a network partition. This means that during a partition, you have to decide whether to prioritize strong consistency or high availability. There are two main consistency models to consider: strong consistency and eventual consistency. Strong consistency ensures that all nodes agree on the order and validity of updates before responding to read requests. On the other hand, eventual consistency allows temporary inconsistencies between nodes and favors availability and scalability. Now, let's take a look at some real-world examples. Traditional relational databases often prioritize consistency over availability. When network partitions occur, they may choose to stall operations until consistency is restored, sacrificing availability. On the other hand, NoSQL databases like Apache Cassandra prioritize availability over strong consistency and are designed to handle large-scale distributed environments. One prominent example of the CAP theorem trade-off is Amazon DynamoDB. It exemplifies the AP trade-off, favoring availability and partition tolerance. DynamoDB allows users to read and write data with low latency, but eventual consistency may result in temporarily inconsistent data during network partitions. To wrap things up, it's important for system architects and developers to carefully consider the requirements of their applications and weigh the importance of consistency, availability, and partition tolerance. While the CAP theorem provides valuable guidance, recent advancements and emerging technologies are pushing the boundaries of distributed system design, offering exciting possibilities for future innovations. That's it for today's episode of Continuous Improvement. I hope you found this dive into the CAP theorem insightful. Stay tuned for more fascinating topics in the world of technology. I'm Victor, your host, signing off.